Hi there, welcome to Unit 6, Part 1. Today we're going to cover reactions of halogenalkanes, and we are officially starting Organic Part 2. Just to give you a heads up, Organic Part 2 is predominantly about chemical reactions of organic compounds sorted by functional group, but will also include a large section in chemical tests and chemical analysis later on in the unit. The way that I had it organized last year, I'll probably be the same this year, is that there will be 7 parts. So this is going to take us, we're going to fly through this information, and it's going to take us to like close to mid-March is going to be around when your exam is. So you'll have 1 month exactly about to wrap your brain around the information here and to memorize all the necessary reactions. So I hope you're ready. Let's go ahead and get started. I'm going to first go over the objectives, which you'll notice are on the back of the first page, and then we'll get to the 2 bellwork questions. For the bellwork questions today, I'm going to pause. I'm going to ask you to answer on Edpuzzle, and then I'll go ahead and I'll go over the answer. And I'll be doing that throughout the lesson today, stopping, pausing, and having you answer on Edpuzzle for participation, and then we'll continue from there. Just also a reminder of the things you will need to do for credit for this lesson. You need to complete the Edpuzzle and answer all questions. You need to get the correct answers down in your guided notes. You need to create flashcards on all of the reactions we discussed today, and then you need to show that to me next week on Tuesday when I am back physically in class. All right, without further ado, let's go ahead and get started. So first, going with the objectives. It says candidates should be able to, first of all, recall the reaction, specifically the reagents, which is what reacts with the organic molecule, and the specific conditions by which halogenalkanes can be produced. And so 15.1.1 is something we did in Organic Part 1. The first way we can make a halogenalkane is by the free radical substitution of alkanes by a halogen in the presence of UV light. And the second is an electrophilic addition of an alkene with a halogen or a hydrogen halide at room temperature. So that's actually something that we've done before. Along with 15.1.2 is nothing new either. Classifying halogenalkanes into primary, secondary, and tertiary types is basically just saying if I have this, a halogen alkane, and the carbon that's attached to the halogen alkane is attached directly to 3 other carbons, this is what we would call tertiary. Whereas if we have this, the carbon that's attached to the halogen alkane is only attached to 1 other carbon. This is what we would call primary. And of course, secondary would be attached to 2 carbons. So that's something that we have sorted in the past. Whenever you see primary, secondary, tertiary, the prediction is always done the same way. And then the new objectives now describe the following nucleophilic substitution reactions. And so today you're going to have your first group of reactions you have to memorize. And yes, you will need to work on memorizing these ASAP, immediately, because your success in this unit is really dependent on you being able to memorize these reactions, and specifically, what do you start with, what do you end with, and what is the functional group change that is occurring. And so we're going to be looking at the reaction of halogenalkanes with NaOH, AQ, versus NaOH in ethanol. And then we're going to look at the reaction with CN, cyanides, and it could be with KCN, but it could also be with NaCN. The group 1 metal is a spectator, and this produces a nitrile. And then the reaction with NH3 and ethanol heated under pressure to produce an amine, and then the reaction with aqueous silver nitrate as a method of identifying the halogen present. Finally, we are going to describe and explain different reactivities of halogen alkanes by referring to the strength of their bonds. And so bond strength, that's actually going to go back to bond energies. And so we've got a lot to do today. Make sure that you are taking notes as you go along, and answering the questions on the Edpuzzle. And I'm going to set it so that you can rewatch it if needed. And then, of course, if you have any questions, reach out to me. I am around. I'm still working today, but I am just not on campus. All right, so let's go ahead and get started. Bell work 1. I'm going to go ahead and pause now and give you a moment to figure it out. Once you answer on Edpuzzle, go ahead and hit continue, and I'll explain the answer. So the question is, what always applies to a nucleophile? So if you'll recall from organic part 1, phile means lover, and the nucleo means nucleus. The nucleus is positively charged, so we are looking for a lover of positive charge. That's the definition of a nucleophile. And so the word always is tricky because some of these are sometimes and some of these are always. What always applies to a nucleophile is it has a lone pair of electrons, because the lone pair of electrons will be what establishes that bond in the mechanism via a coordinate covalent bond. Whereas with a negative charge, some nucleophiles are negatively charged, but not all of them are. Like I've just written ammonia as a nucleophile, and ammonia is not negatively charged, but it does have a pair of electrons to donate. And so that's why the answer here would be B. Let's go ahead and take a look at bell work 2. So bell work 2, I'm going to pause again, and then we'll go over the answer. All right, so take a look carefully at this question. It says, suggest the type of reaction that occurs in reaction 2. So when you are suggesting a type of reaction, it's really important that you look specifically at what changes from the reactants to the products. And so this being your reactant and this being your product. And this is written in skeletal form, but if you want to draw it out, what's at the end here originally are 3 hydrogens. And in the product side, you have 2 hydrogens and a bromine. So a hydrogen has left and a bromine has taken its spot. And so the type of reaction that this is, it's called a substitution. And if we were to further specify what type of substitution it is, and there was another mark here, we would say that it's a free radical substitution. And you could still say that. You could say free radical substitution because we are turning an alkane, a hydrogen, being swapped for a halogen. And remember, a hydrogen swapping with a halogen is always free radical substitution. All right, so that was the bell work. We're going to go ahead and now get into the lesson itself. Ways to prepare halogen alkanes. And so this is review, but you're going to want to write down on a flashcard how to prepare halogen alkanes. And so on your front of your flashcard, you would want to put your reactants, and on the back of your flashcard, you would want to put your products. So if you look at this reaction, let's say that, and you don't have to use the same exact one, but you would say CH4 plus Cl2, that would be your reactants. And then you would have to come up with the prediction that your products would be CH3Cl plus HCl. You can also make another flashcard that goes over conditions. Free radical substitution, conditions, and the back of your flashcard, of course, would say UV light. And you can finally say, in a free radical substitution, so you could actually make 3 flashcards. In a free radical substitution, you start with, and so free radical substitution converts, and the actual conversion that we're looking to occur is that it goes from an alkane to a halogen alkane. That's the conversion. So for every type of reaction, you could make 3 flashcards, one with reactants and products, another with the conditions, and then a third one with the functional group substitution. What functional group do you start with? What functional group do you end with? You need to make flashcards on every single type of reaction that we discuss over this unit. I have given you, it said there was 400 flashcards in that packet with that I gave to you last class period with the little ring binder, so you need to put that together and start writing out your flashcards. This reaction is one from before, from organic part 1, but when you get the exam for organic part 2, all the organic 1 reactions will also be there, because when Cambridge gives a question, they're going to just put all of organic together. So you need to go back and review all of your organic 1 reactions. The second reaction here is an electrophilic addition to alkenes. And so this is the second way to prepare a halogen alkane that was discussed in the standard. And so the 3 flashcards you would make, you could make one that is reactants and products. And so once again, that one would look like you would start with any, and it doesn't have to be this exact reaction, but if you want to use this exact reaction, that's fine. So your first one would be just the reactants on one side and the product on the other. And this is an addition reaction. Then I make a second flashcard with conditions. So electrophilic addition. And here, there really aren't any special conditions. So I would just say electrophilic addition reagents instead, because you would need to know what your possible reagents are, and it would be X2 or HX or H2. There are a few. You'll need to go back into your organic part 1 notes and add in any others. Actually, I would just put X2 and HX. And then the third one would be the conversion. And this one's really important. Electrophilic addition converts. And it's going to be an alkene to a halogen alkane. You're adding to the double bond of an alkene to form a halogen alkane. So once again, you're going to want to make 3 flashcards here. One for reactants and products for an example reaction, one for the reagents. You can also put N conditions, but there's no special conditions here, so you'd want to outline that. And then finally, the conversion, electrophilic addition converts, and then alkene to halogen alkane. And so that's actually review, but make sure that you have it on flashcards. So next, we're going to take a look at the intro to halogen alkanes. All you need to know about a halogen alkane is that it would be an alkane with carbon-carbon single bonds, except there's a halogen added to it. And you could have 1 halogen or you could have more halogens. So there's just, that's all it is. Halogen added to an alkane. There is a general formula for it, and the regular general formula for a alkane is CnH2n plus 2. So I just want to bring that up. Alkane's general formula is CnH2n plus 2. So all you should notice here is that one of the hydrogens is replaced with X, where X represents any halogen. And of course, any halogen that naturally exists. So that'd be fluorine, chlorine, bromine, or iodine. However, they could also theoretically ask you about astatine because it would theoretically do the same things. So, next class period, when I'm back, I'm going to walk through the mechanisms, and it is mechanisms for nucleophilic substitution. There's actually two different mechanisms that you're going to have to memorize for nucleophilic substitution, depending on the identity of your initial halogen alkane. And so now we're into reactions of halogen alkanes. So what do halogen alkanes do? The main type of reaction that a halogen alkane does is called a nucleophilic substitution. And the idea is that there is a swap of nucleophiles, meaning whatever nucleophile was originally on your halogen alkane, which would be the halogen, gets kicked out of the organic molecule and replaced by a better nucleophile. And you're like, wait a second, what? So we have two things here, and in this reaction we have what we call the attacking group, and yes, it is called the attacking group, and we have the leaving group. And if the attacking group is stronger than the leaving group, this is a trend in chemistry, this happens. If the attacking group is stronger than the leaving group, then the attacking group will assume the place of the leaving group in the original organic compound. So you can see in this general reaction in front of you that cyanide, Cn-, and this would be, we would want to have the arrow actually start at a pair of electrons. I found, like usual, this image online, so it's not perfect, but we would want to suffix that to make the arrow start at the pair of electrons. A pair of electrons on the Cn is what you have to notice, and it has to be the one that's on the carbon. If you want me to, I'll go ahead and I'll draw out that Lewis structure. But the point here is that cyanide is a stronger attacking group, and iodine is a great leaving group, and I'll explain why in a moment. And so Cn- attacks the organic molecule and basically forms a bond with the carbon in the middle, but carbon can't have 5 bonds, so the Cn and the I can't both be attached. And between the iodine and the hydrogens, the iodine is going to leave. And so the iodine leaves, and you end up with I- on the product side. And so here your attacking group is Cn- and your leaving group is I-. You will not have to predict if the reaction happens in this course. You are going to be able to assume that if they give you an attacking group and they give you a halogen alkane, that the swap happens. But if you were to study a more advanced version of organic chemistry, we would actually have to determine, is the attacking group strong enough to replace the leaving group? And just for your benefit, I'm going to talk a little bit about what makes a leaving group a good leaving group. Beforehand, though, let's go ahead and draw out the Lewis structure for Cn-. And so for Cn-, I'm going to draw out the Lewis structure. If you draw out the Lewis structure correct, this is what you get. It's actually almost exactly the same as the Lewis structure for carbon monoxide. I'm going to go ahead and show that from scratch. You would have carbon, you would have nitrogen, you would have this. Then nitrogen would get an additional electron because of the -1 charge. And then you would get a bond here, a bond here. And in order to establish the third bond, you actually get a dative bond. And then the electron on the top of carbon moves from here to here. So it's actually literally pretty much the same thing that happens with carbon monoxide, if you recall how to draw that Lewis structure. And the reason we need the dative bond is so that carbon completes its octet. And so it's important to note that the pair of electrons that's attacking with cyanide is coming from the carbon, because the carbon is attaching. So this diagram isn't actually completely accurate because it would be backwards like that, Cn. So you'll want to fix that in your notes. It's not the nitrogen that attaches, it's the carbon. And that'll be shown again later on when we go over the specific reaction with cyanide. So here we were just doing the general. So moving forward, what makes a good leaving group a good leaving group? you can tell by the halogens a general idea of what makes a good leaving group a good leaving group. So we're looking for a large size. And the reason why a large size makes a good leaving group is because it allows the ion to be more stable. So it stabilizes when the charge is spread over, and this is because the charge is spread over a larger area. And once again, this does not have to be memorized for Cambridge. I'm just going over this to help understand what's happening here in the situation. So if you look at the reaction at the bottom, it says that bromine's a leaving group and OH minus is going to usurp bromine's spot, which means that OH minus is a better attacker. And so OH minus will basically take the place of bromine in this compound. So if we add some sodium hydroxide to a solution of that halogen alkane, we will kick that halogen out and make an alcohol. And so this is a way to go from a halogen alkane as a starting group to an alcohol as an ending group. And these functional group transformations are extremely important if you were to study biochemistry or organic chemistry, if you're studying pharmacy or medicinal chemistry. You have to know about these functional group transformations because different functional groups change the function of the molecule, which on a biological level is extremely important. You do not need to memorize this chart. I'll start with that. So I went ahead and I found the pKa table. And pKa, I have not described what that was, nor do you need to memorize what it is, but I am going to state what it is. It would be discussed at the A level, but capital K, we have learned, is equilibrium constant. Ka is equilibrium constant for an acid. pKa is like pH. So we learned in pre-ACE chemistry that pH is the negative log of the H plus or the H3O plus concentration. pKa is actually just a transformation of Ka. It's the negative log of the Ka. And so the reason why people compare pKa's instead of comparing Ka's is because the numbers, when we establish the logarithmic scale, look a lot nicer than looking at 1.7 times 10 to the negative 11, for example. It's easier to just look at the number 10. So that's the idea here. So taking a look at this chart just to give you some idea of what's going on. We know that HCl and sulfuric acid, we know that those are strong acids. And guess what? HBr and HI are very strong acids as well. Not the ones that you need to memorize for this course, but they are extremely strong. Look, their pKa's, which is how strongly acidic they are higher than sulfuric acid and hydrochloric acids, or like more negative than hydrochloric acids and sulfuric acids pKa's. And so take a look at the conjugate base of each of these acids. So if this is a very strong acid, something to take note of is very strong acids produce weak bases because nature favors weaker products. Nature favors weaker products. And so the way to interpret this is weak bases are at the top of the list and strong bases are at the bottom of the list. Strong bases derive from very weak acids. So the conjugate base of a weak acid is a strong base. The conjugate base of a strong acid is a weak base. Once again, not something you have to memorize, but it's just to help you understand what's going on here. And so if you look at this, A weak base is an excellent leaving group. And this is because it can handle being on its own. That substance can handle being on its own quite well. It stabilizes its charge. Look at the bottom. If you look at the bottom, you're going to see some poor leaving groups, very poor leaving groups. An alkane that's lost a hydrogen with a minus charge, this is a poor leaving group. And the reason why this is a poor leaving group, super terrible leaving group, it's not going to leave, is because it's definitely not favored to be that way, first of all. It's going to gain hydrogen wherever it can, or it's going to gain a bond. It's going to bond to whatever it can immediately as fast as it can, because that's definitely not favored. So it's a super terrible leaving group. You're not going to kick it out. Whereas I minus at the top, it's like pretty weak, can handle being on its own, excellent leaving group. And so the ones that we're going to take a look at, and not everything that's in the lesson today is on this chart, but a lot of the groups are. Our attacking groups that we're going to feature today are NH3. We're going to be featuring OH minus, and we're going to be featuring water, actually. And so I'm just circling those because I want to point out that OH minus is actually, if it's a poor leaving group, it is a great attacker. Poor leaving groups are great attacking groups. They're wonderful nucleophiles. They will react quite strongly. And water, you'll see, is actually not a great attacker. However, you will see some reactions with water, but they require stronger conditions for them to occur. Whereas OH minus requires only weak conditions because it's such a great attacker. You don't need to like increase the temperature or add pressure. You don't have to do much for that to happen. It's just going to happen because OH minus is a great attacker. And so this is just some information to add to help you understand what's going on. You do not need to describe any of this for Cambridge. There are no questions asked about attacking groups and leaving groups, but it's just to help understand. So here's what we need to know. And this is the first reaction for nucleophilic substitutions. The first reaction that can happen that you need to memorize is that a halogen, when reacted with an alkali, which is a strong base, will undergo a substitution in water. And so specifically, and so take a look at this. The OH minus is the nucleophile. This reaction does require something called heating under reflux. So this isn't generally true for most substitution reactions. You don't need too high of heat, but you do need to heat under reflux. And you don't need to shout out a specific temperature. You just say heat under reflux. And the setup for a heat under reflux is on the side. And so in a reflux setup, you have water that goes through this condenser. And basically what it does is as your particles are evaporating, the water cools it back down, so it goes back down. So it allows you to heat up your mixture without evaporating your volatile organic compounds so that they could stay in the solution and they're available to still react. So whenever you have, and the reason for this is because this is a lower boiling point than this is, higher boiling point. You don't want to heat CH3CH2Br so high that it all left the container. And so in order to mediate the reaction so you get a good yield, you use this setup called heat under reflux. And yeah, you do need to know those conditions for Cambridge. So the other note here is that the NaOH, the Na plus, is a spectator. So you can write it when you're writing an equation, but it does not have to be shown. It could not be shown, or it could be shown. If you are asked for the ionic equation, it would not be shown. Because in ionic equations, spectator ions are not shown. All right, so what flashcards would we want to make off of this? And now it's going to be time, and you need to make some flashcards for the first type of reaction. First one, if I want to change a halogen alkane, so functional group transformation, to and this is an alcohol, and put in the back, the reagent is OH minus, and also you could do this with water. But I would say actually to wait to write that because we'll see it later on because the conditions might be slightly different. So the reagent is OH minus, and the conditions, aqueous, meaning in water. Your base is in water. And this is going to become really important later on, and you're going to see in the practice questions that something different is going to happen in water versus in alcohol. Aqueous, conditions, and heat under reflux. So that would be the first flashcard I would make. The second one I would make is an example reaction. And so just something like CH3, CH2, CH2Cl plus, this is actually not a great leaving group, but we're just going to assume that it happens, OH minus, and then the products of that reaction would be CH3, CH2, CH2OH plus Cl minus. And so once again, one side of your flashcard would have your reagents, and the other one would have your products. And then I make another for the functional group transition, which is the one that tells me when I want to go from a halogen alkane to an alcohol, what do? I need the reagent OH minus, because that's going to swap out and get rid of the halogen and replace it with the OH. And the condition is aqueous with heat under reflux. So at minimum, for each of these reactions, I would suggest 2 flashcards. So if you go back to the standards, they do ask you for the relative rate of reactivity. So although they don't ask you what's a better leaving group and what's a worse leaving group, they kind of do, but in a different way. And they ask you to explain in a different way than what I told you earlier. And so let's talk about this. Using different halogen alkanes, the reactions will proceed at different reaction rates, meaning some reactions will happen quicker than others, depending on how easy it is to break the bond in the mechanism between the carbon and the halogen. How easy it is to break the bond will determine reactivity. So what we use is we actually use a chemical test. We use AgNO3, which is silver nitrate, to test the rate of the reaction. And you are going to, in Unit 7, the final unit for this class, which is next unit, you are actually going to have to memorize the colors of all the precipitates formed with halogens and silver. And so AgBr, AgI, and AgCl all form solids in solution. You'd visibly see a solid forming. So as the reaction occurs, you'll start to see the production of a solid, of a precipitate. And this will take place at different rates with bromine, with iodine, and with chlorine, because the bond energies of CBr, Ci, and CCl are all different. And so the test results I already have here, and I'm going to describe it on another slide with a little bit more detail. But the test result is that the fastest nucleophilic substitution reaction takes place with the iodoalkane, meaning the solid forms quickest with an iodoalkane. And the slowest nucleophilic substitution takes place with fluoroalkanes. Believe it or not, iodine and fluorine are both not great to work with. I think of it, I liken it to Goldilocks. If you remember that story, not too hot, not too cold, not too fast, not too slow. And the problem with iodoalkanes is they produce the product too fast. And so the reaction's a little bit more violent, and you could have some byproducts. And the slowest nucleophilic reaction, it basically doesn't happen. You don't get enough yield for it to be worth your time and effort. And so usually when we look at examples, we are almost always going to see them with chlorine and bromine because they're right in between iodine and fluorine in the halogens, so not too fast, not too slow, not too hot, not too cold, that idea. So this is what I'm talking about with bond energies. The CF bond energy is much larger, meaning it requires a lot more energy to break the bond between CF than it does to break the bond between CI. So it would require the strongest conditions. This is going to be the least reactive, the slowest to form precipitate when adding AgNO3. And this would be the fastest to form precipitate. I do want to remind you, because we are on Nearby, you can pause this at any time. We're on Edpuzzle. You can pause this at any time when you need to continue to take notes, and then continue. So here we go. Example reaction. This is a reaction of CH3CH2Br with water, and you end up with a substitution, bromine for an alcohol. And we want to trace how slow or how fast this reaction takes place. And so what happens is you add AgNO3 into this mixture. And so you'd have CH3, CH2Br, you would have H2O, and you would have AgNO3 in the mixture already. You would just place some silver nitrate in that mixture. And so what happens is as this reaction takes place, and specifically as the substitution happens, Br minus reacts with Ag in the AgNO3. AgNO3 is soluble in water. Silver nitrate breaks apart in water, but AgBr forms a solid. And so if you've got Ag plus ions and NO3 minus ions in the solution, AgBr is going to connect together, form a solid. And how quickly this happens determines the rate. And so once again, what you need to memorize is that the CF substitution would take place at the slowest rate, and the CI substitution, where iodine gets kicked out, that would take place at the fastest rate. Also note, and I wrote it down here, the reaction takes place slower than the reaction of OH minus, and this is because hydroxide is a better nucleophile than water. So why does, I already answered this, because OH minus is a better nucleophile, stronger nucleophile than water. And then explain why silver nitrate solution can be used to investigate the rate of hydrolysis, include ionic equations for the formation of the precipitates. And so I already explained this as well, but just to show you an ionic equation for the formation of a precipitate, an example would be Ag plus Cl minus AQ goes to AgCl solid. Ionic equation means we are only looking to put the ions together that actually form the solid, and we don't include any of the spectator ions. This is actually something I've seen not only on paper 2, but I've also seen this on paper 3, where they'll ask you for an ionic equation. And so recognize that when we do get to qualitative analysis, which is going to be our final type of lab, and we're going to do that in Unit 7, you will see ionic equations asked for like this. All right, reaction number 2, substitution with cyanide, Cn minus. So you can, because Cn minus is an excellent attacking group, and I would encourage you for this nucleophile, go ahead and write a pair of electrons on the carbon, because that's the pair of electrons that is going to reach out, grab the carbon, and then the result is, in this case, the bromine gets kicked out. And so this is the conditions in ethanol. This is a condition, and this is a condition. And the reagent is some kind of Cn minus. It's also important to note that this is the only type of nucleophilic substitution reaction that you actually add an extra carbon atom to the original chain. So you lengthen the carbon chain when you do a substitution with cyanide. And sometimes it is important to lengthen the carbon chain for different reasons. And so this is a tool in the toolbox to lengthen the carbon chain. So let's take a look at what are the flashcards we should make. One flashcard you should make, and I'm going to go ahead and create another slide here. Insert, just to show you. So one flashcard you should make is halogenalkane to nitrile, the functional group transition. And then on the back, you want your reagents, conditions. So your reagent is whatever reactant you have to put with a halogenalkane to make that reaction happen. And so the reagent you would need here is Cn minus. So it could be NaCN or KCN or LiCN. All of those group 1 metals are spectator ions and may or may not be shown. The other thing is your conditions. You are reacting it with ethanol as a solvent, and you are also heating under reflux. I would then make a flashcard with an example reaction. Doesn't matter what you do. You could do CH3Cl and then plus Cn minus, and then you get CH3Cn plus Cl minus. Oh, on the other side of the flashcard, sorry. So on the other side of the flashcard, you would have the products of this reaction, which is CH3Cn plus Cl minus. And then I'd actually make a third one for this one. And the third flashcard that I would make is, I would do how to add carbon to carbon chain. Only happens in reactions with Cn minus, because the carbon adds to the carbon chain. And this isn't the only reaction with Cn minus. There are others later on, or there's at least one other later on in this unit. So I'm just saying that if I want to add a carbon to the carbon chain, I'm gonna need a reaction that involves the cyanide ion. All right, we're gonna go ahead and continue. We have another reaction to go over. And so the next reaction is substitution with NH3. And so for substitution with NH3, we have another nucleophile. And our nucleophile here is NH3, and the part that makes this a nucleophile, the part that's gonna attach, is the lone pair of electrons on the nitrogen. And so in this nucleophilic substitution, it's a little bit interesting because when the NH3 attaches and the bromine leaves, you also have, and it would be more covered in a mechanism, but you also have that you are losing one hydrogen, and that one hydrogen is actually connecting with the Br minus. And so you end up with CH3CH2NH2, so it doesn't have a charge, and an amine, and you have HBr as your other product. And we would call that just an inorganic product. And that's a strong acid. Oof. Conditions: heat, and then I would actually say ammonia is a reagent, but dissolved in ethanol is a condition. And then this was mentioned in the syllabus standards. You also need to remember this takes place at a high pressure, but you don't need to memorize an exact pressure. If the ammonia is not in excess, so you may want to say excess ammonia here. Because if the ammonia is not in excess, you could get a mixture of products because the amine you make could attack another halogenalkane and continue to, almost kind of like the same idea as propagating, give you additional amines that are different. And so you do not need to memorize that. But the idea here is that you would want excess ammonia. That I would suggest knowing. And so once again, we're going to trace through flashcards to make here. The flashcards to make for reaction number 3. First thing I would say is halogen alkane. I start with a halogen alkane and I want to go to an amine. How do I get there? Reagent is what do I need to add? And that's going to be NH3. Conditions, excess, dissolved in ethanol, and high pressure. And yes, you do have to memorize the conditions, and that's what makes this unit a little bit tricky because there are a lot of marks for reagents and conditions, so make sure you start working on it now. That's why I'm having you create the flashcards instead of having you do an assignment. You'll have an assignment on next class, but today is to get the flashcards started because this is something you're going to need to keep up with throughout the unit, and you're going to need to review every day for a little while just to practice memorizing these reactions. Okay? The next one I would do is a practice reaction. So it doesn't matter. You could do CH3, CH2I plus NH3. And then that would be my front. And then my back would be CH3, CH2, NH2, and HI. Because you remember, it goes from NH3 down to NH2, and the hydrogen joins with the iodine leaving group. Those would be the 2 flashcards that I would create for this reaction. You can create more flashcards if you like. This is just my suggestion, and make sure that you're doing that because I am going to be grading as an assignment grade that you did take the notes and that you are making the flashcards. And I'm going to talk more about those flashcards because they're going to be additional grades in this unit. It's so incredibly important that you are practicing and revisiting these reactions over and over again. Okay. Time for a practice Cambridge question. And so a lot of what the rest is, I have one more type of reaction to go over, but practice Cambridge question time. Which reactions are examples of a nucleophilic substitution? I'm going to go ahead and pause and let you think about that and then answer, and then I'll tell you the answer. So, did you get it right? Reaction 1. That's a nucleophilic swap. Yes. Reaction 2. OH minus an iodine swap. That's a nucleophilic swap. And reaction 3. That's the one we just looked at, I believe. Nucleophilic swap. All 3. And so the next checkup, explain why ammonia and amine molecules can act as nucleophiles. Go ahead and answer, and I will pause again. To help to answer the question, I would actually draw ammonia, and I would draw an amine. And I'm drawing the fully displayed versions. And I'm doing the simplest amine because I don't want to do extra work. I just want to do enough to give full explanations. And so why can both of these act as nucleophiles? The reason is because both ammonia and amine have a lone pair of electrons. Both ammonia and amines have a lone pair of electrons to donate. And that's why. All right, so final type of reaction for today. And remember, next class, when I'm back in class, we're gonna go over the mechanisms for for nucleophilic substitutions. You do not have to memorize the mechanism for elimination reaction. However, I do have it here if you like to see it. But you don't have to memorize a mechanism for elimination. It's not in the standards. Halogenalkanes undergo elimination reactions. Just to recall, an elimination reaction is where you end your product is an alkene. There's a double bond in your product. And so two groups are removed, and that's why the word eliminate is there, and you get a double bond. And so for an elimination with a halogen alkane, you need to memorize the specific condition that Cambridge requires you to know is that the solvent, instead of being in water, the solvent is ethanol, or you could even say alcoholic, not what you think, or ethanolic. So then you will be required to know if you have NaOH, AQ, a substitution takes place. But if you have NaOH in ethanol, an elimination takes place instead. I added in a little bit more. This I got from the study guide for AS chemistry that somebody had made. Like, it was a book I had bought, and so I got some information here, but this is, again, to add to your understanding. Elimination reactions require a higher activation energy than substitution reactions. Therefore, higher temperatures favor elimination. Steric hindrance means bulky molecules. Due to steric hindrance, because it is hard to get a swap to occur in a tertiary halogen alkane, instead elimination is favored. And then finally, we haven't talked about SN1, SN2 reactions, but it is interesting that they involve degrader spreading out of charge. So they're favored by less polar solvents than water. And ethanol is a less polar solvent than water because of the additional carbon groups that are nonpolar. So let's take a look at a Cambridge question. Actually, let's go ahead and make a flashcard real quick for elimination. So, flashcards for elimination reactions. First one, halogen alkane. How do I get a halogen alkane to become an alkene? I'm going to go from a halogen alkane to an alkene. Our reagents and conditions. So, reagent, NaOH, or KOH or LiOH. Again, the positive ion is a spectator. But the condition here is really important. The conditions, ethanol, solvent. And you can just say ethanol, in ethanol. And I would also say high temperature, but I don't always see a mark for that. I would just put it because it is supposed to be high temperature. And that's because they have a high activation energy. The other thing I would do is I would do an example reaction. So I would have like CH3, CH, Br, CH3, and then plus NaOH in ethanol. And then on the other side, I would put CH2, CH, CH3. It doesn't matter if you put the double bond on the left or the right side. That doesn't matter because they're equivalent on either side. But you could have non-equivalent products as well. And actually on the flashcard where you did substitution with OH minus earlier, you probably want to write aqueous. So let's take a look at some Cambridge questions. As usual, I'm going to go ahead and pause, and then I'll answer each one. And these are the last few questions we're going to do for today's lesson. I have 4 of them. 2 of them I realized were exactly pretty much the same. A reaction occurs when a sample of 1-chloropropane is heated under reflux with sodium hydroxide dissolved in ethanol. Which row is correct? So you're looking for dissolved in ethanol. That favors elimination. And then if I have 1-chloropropane, and I'm drawing out the whole thing, but you do not have to. In an elimination, what happens is the 2 groups next to each other would be taken, so you would get this. And that answer is propene. And so here we would pick B. To show this in skeletal version, which you could totally do, it would look like this. The conversion taking place. Next question. Almost the same exact question, believe it or not. And yes, there's only so many different types of questions they can ask. If you understand the idea of what's going on, hopefully it should be relatively simple to solve. Again, we're going to take, and it doesn't matter which hydrogen we take because it's equivalent on either end. So we're going to do this, and then we end up again with propene, which you do not have to do displayed. You could do it skeletal. Yeah. And so we get propene. Third question. A little bit trickier. And because we haven't quite done the mechanism, it won't be completely apparent. However, you can use the ideas we learned in organic part 1. The most stable carbocation would be the most substituted. So we're looking for a tertiary carbocation. And so the only option that gives us a tertiary carbocation is this one, which is 2-chloro-2-methylpropane. Final question. This one's a tricky one. For which reaction will the major organic product have the lowest relative molecular mass? And so I was working this one out, and it is tricky. When you do each one, you have to do the substitution or the elimination. I'm going to tell you real quick the molar masses of the products for the 3 that were potentially the answer. The molar mass of this product is 46, of this one is 45, and of this one is actually 42. I'm going to go ahead and show D because that's the answer. So we've got 2-bromopropane. Right? And so we have ethanol, sodium hydroxide, so it becomes propene. And then we have to get the molar mass of propene. The molar mass of propene, it's 3 carbons and 6 hydrogens. So 3 times 12 plus 6 times 1 is 42. Just for posterity, I'm going to show you A. So looking at A, bromoethane. It's heated under reflux with OH minus, and so substitution takes place, and you get, instead of the bromine, you get an alcohol here. So we would have C2, H6, and the molar mass of this would be 12 times 2 plus 6 times 1 plus 1 times 16, which is 24 plus 6 plus 16, which adds up to 46. And so they made the answers actually all real close here, which makes it quite tricky. But the answer here is D. So it's a bit of a Cambridge time waster type question. All right, we're going to stop here. On next class, we are going to take a look at additional practice questions with nucleophilic substitution, and we will go over the mechanism. I hope you were able to grasp the information in this lesson, and if you do have any questions, let me know. Make sure to bring your completed guided notes with your answers to the questions and the added notes I put in to fill those in, and your flashcards on Tuesday because I will be checking them during bell work time. All right, have a wonderful day, whatever day you're watching this, and I will see you next week.